Good morning. Let us start another lecture on stress strain diagram for mild steel and applicability of the Hooke's law. One must be able to understand this diagram properly to understand the behavior of material under the application of applied load. Now on this right side I had drawn this uh, stress strain diagram. Now there are two diagrams. One is this solid one, as you can see this black mark, and another one is this dotted one. This is this one. This solid one is represent true stress, which we had learned in our previous lecture, that what is true stress and what is engineering stress. Sorry, this solid represent engineering stress. Solid line represent engineering stress, and this dotted line represent true stress. One more concept is there, to which we call strain. Let me discuss this. In last lecture it was not discussed. For example, there is a rod like this, and we apply some normal load P, and under the application of this load, that this side is fixed, its dimension increased to some extent. The increased area is represented like dotted one, like this one, like this one. So original length was L, another length was this L plus this del L, which is increased under this load. So strain is represented by epsilon. Strain is equal to change in length, which is this del L divided by original length L. This is known as strain, right? If we multiply it by 100, then it will be percentage strain in terms of percentage, right? Now in this stress strain diagram, this stress strain diagram is for mild steel, number one. Now what we see, what are different points of interest on this stress strain diagram, we will study. Now first of all, point number O to A, we can see up to this point. This is up to point A, OA. The OA line is very straight line. It is a straight line. Straight line. So this straight line is known as proportional limit. A is known as the proportional limit. This Hooke's law, this particular Hooke's law is valid within this straight line up to A. However, the region between A and B is curved. This is curved. This is not a straight line. This is curved. The point B is known as the elastic limit point. The point B is known as the elastic limit point. So point A is known as the proportional limit, right? And point B is known as the elastic limit, right? Now the material will come back from point B. If we put a load and increase load so that material is strained up to point B, then if we release load at point B, then material will come back to its original position, right? But the Hooke's law is valid only up to point A. The Hooke's law is not valid up to point B. Hooke's law is only valid up to point of proportionality. Now the point C is known as the upper yield point. In case of mild steel, the sigma of Y steel is equal to 250 megapascal. This is equal to 250 megapascal in case of mild steel. This you can remember this. In most of numericals you will find this particular value. And E for steel. E is the Young's modulus. We will discuss when I will explain about the Hooke's law. For steel, steel is 2 into 10 raised to power 6 kg per centimeter square, right? This is the E for mild steel. In most of numerical you will find this value until and unless some another grade of mild steel is there, right? So this is upper yield point, this is lower yield point, and after from this C dash to D, this particular line is known as the yield plateau. Here is much more fracture strain under the application of same force, means there is not increase in force. We applied a force up to this point. After this point there is slippage start, and after that, under that particular constant load, there is deformation. And after D to E point there is necking in the material. E is the point of necking, and there is increase in strength of the material. We find that after this, again material provide a resistance to deformation. This particular region is known as strain hardening region. When I will teach material science, then I will tell why the resistance of material is increased in this region. After that, this particular region is known as strain softening region. Up to this point, material is providing more resistance to deformation, but after this, material is not providing much resistance to deformation, and this is the point of fracture. And the strain material occurred in the material up to this point is known as the fracture strain. We will see in our next lecture also that how increase in carbon percentage in the material make an effects on the fracture strain, how fracture strain is reduced on increase in the carbon percentage, and the strength of the material increase, and up to what point, and what kind of fractures could be there in the material after increase in carbon percentage, and what kind of fracture will be there in the material if carbon percentage is low. Normally, this is a very amplified version of this stress strain diagram. If the rate of loading and its impact is more on the universal testing machine on which you put this sample, this is universal testing machine or universal tensile machine. This if the rate of loading is more, then these points will not be visible. These points will be visible only when the rate of loading is very small, right? Now next, so this is the stress strain diagram for mild steel, and in case of true stress, the curve is increasing constantly, up and up. The reason is area is continuously decreasing, so in so the stress is continuously increasing, right? Now in Hooke's law, we will see that stress is directly proportional to strain, right? This is Hooke's law, but this particular formula is valid only up to limit of proportionality. Normally students get confused, they see that this is up to elastic limit. No, Hooke's law is valid only up to proportional limit. But in case of mild steel, the point B and point A are very close, and if rate of loading is too high, then these two, it is very difficult to differentiate between these 2 points, right? Now if I put the proportionality constant E, then sigma will be equal to E multiply with strain, or E will be equal to Young's modulus, which is equal to stress by strain, and the value of E for mild steel is this, right? But when we gave this, then there are certain assumptions an engineer must keep in mind. That what are these assumptions while deriving this stress strain formula? Number one, material is homogeneous. This is first assumption, that homogeneous, that the material is homogeneous means on every section of material it is mild steel. It is not like this, that here are some like blowholes in the material, or here density is more, here density is less, like this. So material is homogeneous. This is first assumption while giving this statement. And another one is that material is isotropic. It means same property in all directions. Here it means that same property in all directions. If this is a material cube in 3D I draw, then if I strain it in this direction, then property are same. In this direction, property are same. In this direction I strain, then the properties are same. For example, if there is wood, then wood is a non-isotropic material because the fibers of woods are like this, and all these are joined. Now if we pull it in this direction, then the wood will be more strong and will provide more resistance to deformation. However, if we provide force in this particular direction, then the material will fail, then this wood will fail. So wood is a non-isotropic material. So Hooke's law is valid only for isotropic material and not for wood. This is another assumption. Another assumption is that material is linear elastic, right? One is, this is isotropic, and another assumption is material is linear elastic. Linear elastic, right? This line is very important. Reason being, this Hooke's law is valid only in point O to A, right, for mild steel. But if there are certain material which are non-linear elastic, they are elastic, limit is there. For example, natural rubber. This is stress strain diagram for natural rubber. The like this, it is proportional limit is very near to this OA is very near to each other, and elastic limit is up to point B. If we strain material up to point B and after that we release the load, then material will come back to point O, back in its original shape. However, this line is not a linear line, it is a curve. So Hooke's law is not valid for this particular curve. Hooke's law is only valid up to point A. So in this particular case, Hooke's law is valid only when the material is linear elastic. So I thought that one is able to understand, and this value for mild steel is 350 megapascal. Normally this is the point of necking where the material start breaking, and after that neck propagate and the final fracture takes place at this point. We will see what kind of fracture occur and how we can identify the mode of failure from by seeing the fracture type. Okay, I hope you understand this fully.